So, hello everyone. We're going to start the lesson related to structuring the game logic, which is also is another facet or perspective for structuring games. So, one is just how to make the game enjoyable, or how to make, for example, structuring a game from the storyline perspective, which is more a narration perspective of designing a game. And here is just, is the game achieving something at all? Because despite you might provide a very convoluted story, then you need to also ensure that the game is progressing and the player, by achieving the goal, is actually going to finalize the game. In order to do this, then we need to take inspiration from how AI is actually structuring problems with a notion of goal to be pursued, so to effectively assess whether the set of actions that you're going to provide are going to fulfill the game. And definitely the thing that we're going to see is also how, by even taking the same probabilistical distribution on the number of the possibilities, but by changing the type of actions or the configuration of the world, then you might have like a different outcome or expectations on the time required to solve the game. So, and this provides actually an overall view. Then, in order to, so all the things that are explained in here are also provided in the code base. So if you are going in, so in your IDE and you're going to look at the probabilities.cs class, then that is actually going to run in practice all the code that is actually associated to the slides. And I actually already provided, now I forgot to do in the previous years, a handout providing an explanation of what the code is doing. By the way, a deep understanding of a handout is not required. So the detailed explication of the code base. So I provided this handout. There are actually 23 pages, and I'm not, so that is not going to be, so the in-depth characterization is not going to be like part of exam. So it's going to be better just to have like the general understanding that you have from the slides, but this is actually useful if you want to know better, or if you want to clarify some of the topics that we're going to discuss today. So basically that PDF acts more as a comment to the code that I was providing rather than anything else. So this is actually part of the slides that are by Graham Morgan, but I added the code and changed some of the setups. So usually you have also the notion of randomness, which is somehow ill-formed or ill-stated, especially from the simplistic point of view. So randomness is actually something chaotic, disordered, something not necessarily, no, actually, not generated by a decidable algorithm. So that is actually the notion of disorder. Then, in order to have an understanding what disorder might look like, you have, for example, nowadays you have like digital TV, so you do not have any more like what is called analogic television. But in the older days, or if you still have digital analogic radio, then on some stations, if you're tuning, you could see a specific sound, or even if you're looking at the screen, you're seeing actually a lot of white and black pixels roaming around. So that is actually your TV sampling some of the background radiation from the Big Bang, and also, especially if you're seeing that in a store, but then you see that you might see some of the dots being brighter than others. And that is because basically the thing that you're doing is you're sampling some of the waves that the antenna is detecting, and you're having something like a homogeneous representation. So that is actually a visual representation of something randomic. So another way that the computer, very low level, so at the operating system level does, without a specific algorithm, is, for example, just to sample the operations that you did on the keyboard, on the mouse, for example, sampling the heat from the CPU, or all those kind of values, shuffling them around, and then providing you those values. And that provides actually the randomic distribution. So apparently those values are not correlated to each other, and so they act as random numbers. But even something very complicated for which you cannot grasp all the underlying behavior might seem as a chaotic and randomic. So definitely if you're doing like the weather forecast, and if you try, so you have like the Boltzmann equations for volume, pressure, or something of the like, and then you have like the Brownian motion of the particles. And potentially, if you're able to predict all the possible motions of all the particles, then you could provide like potentially a correlation to the other equation, but that is still unknown. And why? Because definitely in realistic case scenarios, you need to predict all the possible movements, consider a lot of variables, which is unfeasible, so it's better just to approximate something with a probabilistical distribution. So, and that is actually what is going to happen. So, sometimes it is a way to neglect or summarize complexity. And on the other hand, you might create a system which is very rational, and so if you're becoming too rational, even in the true life, then you're going to be very predictable. So how to avoid predictability is to adding some kind of variety within the behavior, so choosing a random action, which is still fulfilling your aim, for example, but maybe not providing the optimal solution, a suboptimal, but still is going to do the trick. So you are going to puzzle your opponent whilst you're aiming for your goal. So, and everything boils down to the theory of probability, which I'm summarizing because you don't have a module on probability theory in here, so it's a very quick understanding of that. So if you're taking, for example, a die, then a die has actually 6 faces, which are going to be numerated from 1 to 6. And then you see that the probability of having the turnout of each of the numbers is actually 1/6, because you have 1, which is actually the number that is going to be returned, and 6, which are actually the outcomes that are possible. So you have like the probability of 1. So if the die is is perfect and it doesn't have, for example, it's not tricked, then you have like a uniform distribution among probabilities. But the idea is, and then similarly, you could also have like a pair of non-rigged qubit dices. So in here, then you want to get the probability of getting a specific pair. So 1, 1, 1, 2, 1, 3, so on and so forth. And which is order. So you are always aware of which is the first die and the second die, which is also important. Otherwise, if you're shuffling those around, then the distribution changes. Okay, so under the assumption, but you could always determine which is the first die and the second die. So it's like throwing them separately. So in this scenario, why my probability becomes 1/6 squared? Because then you have 1 of the 6 possible turnouts times 1/6 possible turnouts, and those 2 events are completely independent between each other, because the throw of one die is completely independent from the throw of one die in the best of a possible world. So there are no correlation. So we don't have a joint distribution. So the scenario in probability theory is just the multiplication of the 2 probabilities, which is not necessarily true in the generic scenario. But so the idea is then, next time I will do. So, and then the other thing is you could also create a random distribution, even though it is not uniform. So there is one misconception which is fairly common in video games, that something is random if it is uniformly distributed, which is not true. So one example is, for example, if you want to have like the distribution of all the events where, for example, the sum of the faces of the two dices are summing up to a given number. So in this case, as you will see on the handouts, you will have like a normal distribution where you have like the most frequent value will be like the median value. And then, for example, 12 will be at the very low end because you only have one possible configuration for obtaining that sum. While on the other hand, the median value, which is actually in this case, is actually 6. You have more combinations of dices providing that value. So that you will have like uniform distribution, and still it is randomic. So it's not that all the random distributions need to be uniform. So that is just how the values are provided. So that is actually the likelihood of returning one value. The randomness refers to the way I'm returning the values rather than to the uniformity of the distribution. So what is actually the intuition? The intuition is that you are an observer and you're seeing the values being provided by, in this scenario, like a pseudo-random algorithm, which is deterministic all the time. If not sampling something, then you have pseudo-random algorithms, which are providing you a distribution of numbers. And by looking at them and then trying to guess the behavior, then the best you could say is that the way the numbers are generated is random. But as a consequence, a random distribution does not guarantee to always provide unique elements. Because as an intuition, if you want to just roll a die, then all the numbers that could be generated are just the numbers from 1 to 6, so eventually they will repeat. But the important part is the variety of the numbers, not actually the values that are provided that needs to be unique. So, and that is actually also relevant in video games. So even in video games, the important thing is how the values are returned, the variety of them, rather than the unicity of the behavior, because you're going to have definitely the same set of actions that you want to do to an agent. And that is actually then going to the notion of event and what is that about. So you could, because actually that comes into place definitely if you have like a runtime game and then you want to discretize that using the algorithms that we're going to see. So an event is any kind of action which is performed by the player. Or for example, in a combat game, I'm doing like a right kick or a right punch, and then, or for example, any non-player character providing an answer to the player's action, or independently from that, doing an action nevertheless. And then any change of state of the environment. As we're going to see, even the environment itself might change as internal status do, for example, you are using a random number generator and then you decide to change something from the environment, and then that might force the player to change the plan of action. So for example, I'm taking a path and I want to reach a destination, but then suddenly one road is blocked because I have an obstruction. So then I have a change of state. That is also an event. And then the most important part, which is also related to distributed computation, is that in order to know the principle of causality between this, then you need to first determine how those are correlated to each other, and in this scenario, we're going to simplify that, how those are correlated temporally. So I'm having something, then I'm having that something will happen eventually, and that, and then we have causation. So only because I receive an answer, I might assume that might be related, not necessarily true. That needs to be assessed on average, but we might imply that that answer was a reply to a causation to an event that the player provided. So given this, otherwise it would be always determinable. So that's why, for example, state machines might be quite boring eventually because we are providing always the same behavior. So if you're adding, for example, even to a state machine like a random number generator, and depending on that you're deciding one action, then you're still adding variety. That is actually fulfilling the first bullet points below. And even in there, then you could also associate to human players random number distributions. So that's why, as we were discussing for the first lecture, then in order to analyze and discretize the set of actions, we might discuss just from the notion of turn and assess that one player or one non-player character or the environment performs over itself or over the player some kind of actions. So then, as a consequence, you are subsuming the notion of a turn that is actually provided. So in here, we are also providing a lot of simplifications, because this is actually not a module on artificial intelligence, but it's a module on games. And so we need to restrict our analysis to something manageable to do in less than half of a semester. So in here, we're just going to consider discrete games where you have all the actions that are marked by turns. So you're doing one action completely, for example, and then happens in a specific instant of time, which might be assessed to an integer value or to a natural number, even better. Then we might consider one single agent or an interplay of multiple agents, as we're going to see, that might be still represented as one single player overall, even though they're interacting. The idea is that if you have even two state machines, as I was doing in a master degree dissertation, and you're orchestrating that, then you are like generating one single state machine, where you have all the possible interplays of actions, but that is actually quite unmanageable, so you need like a engineering system orchestrating all this kind of operations. And then we're assuming that all the actions are known, so we can predict the possible behavior. And that is actually also a fair assumption in video games, where you have a player and a non-player character which have a presetted set of actions on which we are going to perform actions. So we're not going to assume that I might do something which is unforecasted or unforeseeable, but we are assuming also in a video game that all the actions that are possible are known somehow. And the set of actions is finite, otherwise you will have like an infinite state of space to crawl, and that is actually non-manageable and is also non-realistic in video games. Furthermore, then we want to define a strategy. So this terminology is also quite different if you're using like reinforcement learning, which is non-overlapping and maybe contradictory, but that is actually the original terminology from AI that then evolved in time. But anyway, in here, we're going to assume that the behavior is episodic if all the actions that you're doing now are not implying any kind of the actions that are going to be performed in here. So any action has no consequence in my future. Otherwise, something is sequential if the order that I'm providing the actions is somehow relevant, and that might dictate my progress or not in the game. And we're going to see an example in visiting a room eventually in this slide. So, and then the thing that we're interested in is in a pattern of events, which are just a subsequent set of actions collected that describes actually the behavior of the player. So that is actually not necessarily related to the game, but the research that we are conducting. So we have a tool where you could log all the actions that are performed, and you could extract rules. If you have this action, then I'm assuming that another thing will happen in the future. So the other thing that we're also doing is, for example, the AI needs to have enough memory to recognize all the possible actions, otherwise you have like zero knowledge or zero memory AI. But in this scenario, we're assuming that we might hold some memory for making inference, and that our environment is fully observable. That is also important. So what does it mean that you have a fully observable environment? Like the non-player character in a fighting game knows the health bar of the opponent, the non-player character and the character know the actions that they might be provided. So, or if I'm exploring a world, like actually I'm crawling a map, which is known in advance. So it's not, for example, that they need to explore something. Then any kind of more realism that you're adding in order to know, okay, something is unknown, then will make the game less predictable, less solvable, and more computationally challenging. So for the purpose of this set of lectures, then we're going to refine some kind of assumption to the bare essential, which is still providing some interesting thing to observe. And definitely how we might achieve a variety, either by adding probability or by providing a set of behaviors which is substantial, so I could create a lot of possible outcomes. So if in a fighting game the only thing that you can do is punch, and I could always detract from the game a given amount, which is always deterministic, then the game becomes boring. So I would know that I need to punch him a given amount of times, and then eventually the game will finish. Otherwise, if I'm adding a variety of set of actions that I can do, cannot do, then I'm adding variety to the game. So even though the game is completely somehow deterministic, I have a lot of interplay of actions that I could perform, and therefore, as a consequence, I have something which is more interesting to do. Still, there is actually a problem when defining a game. If you're providing a too narrow set of rules, then the game will become less interesting, because, as I was saying before, the only thing that you're doing is punching someone and then the game finishes. But on the other hand, the game might become daunting if you're providing a lot of actions, which are a plethora of actions among which I could do whatever that I prefer, and then actually you're puzzling the player, especially if it is a novice, and therefore is actually detrimental for the game. So in medias stat virtus, therefore, is always good to have like a in-between set of features to be combined. Otherwise, we might lose the information whether we are designing the game as we were expecting, or whether we're doing something which is completely irrelevant. So in here, we're not going to assess patterns within video games, but that might be also something that you might want to do a dissertation on, but that should require initially logging the data from your game, so logging all the actions, and then on top of that, then you might infer strategies, for example, and associate different strategies to different players. But anyway, then the other thing that we're going to assess is actually the notion of state progression. So we are progressing within the game if we're actually changing something, and that might be, for example, the life bar. So if everyone is trying to hit some action, but they are completely far from the opponent, I could also kick or punch however I like, but the game is actually not progressing. I need to have an interaction. So no matter how I'm doing actions, those are not relevant to the progress of the game, and so those are completely irrelevant for determining the correlations of the action. So nothing is happening, and nothing is there in the environmental sense. So within this lecture, we're always going to have the scenario on top, which is actually an oversimplification, because the actual representation of the scenario is going to be more convoluted than this, but to represent graphically, but that should be like a good in-between assumption. So just to provide like a better graphical rendering, in order to visualize the game, I was merely using like a housing designer, so to speak. So I didn't want to use like a convoluted asset to do something. So we have this scenario, basically, where each state of the graph that I was showing before, so we have like 4 states, 4 rooms, which are adjacent to each other, and we have 6 doors that, if completely free, so if I'm not require that only one of those doors is actually leading to the next one, then they are going to communicate between each other. But then, the interesting thing that we're going to see is that we always have 6 choices, but we are going to change within this setup the way that we are imposing the choice to the player, and that by only changing this configuration, how the doors could be locked, unlocked, or accessed, or whether I might retain previous information of which was the correct set of configurations, then we're going to experience different ways to assess the feasibility of a game from a probabilistical perspective. And so in here we have always, over time, the 6 doors, and those in here are graphically represented by the 6 edges, which are enumerated 1, 2, 3, 4, 5, and 6. And then, as a first restriction, we might say that some doors are locked, or only one specific door configuration is the winning one. So I'm winning not only if I'm reaching the final state, but also if I'm traversing the correct door. So then in an actual graph configuration, you need to have something more explosive, which in here is very quite simplified. Okay? But that provides also a good way to discretize and discuss what is a game about. So that is actually the way to characterize a game with a notion of goal and set of actions. So a game is always described, and that is important, with a state space. So you have like set of states where you might be at, which in this scenario might be simplistically enough just the rooms where you are. And then you have like initial state, so where you are starting in the game, because actually that is relevant. You might, for example, directly start at the very final door and then the final room, and then you're already finishing the game. But that is actually non-relevant for us. Then you have actions that for us are just picking the door, and actions is not necessarily related to transitions, but in this case there are. So I might have that by picking one door, then I'm transiting from one state to the other. It's going to be more complicated than that in realistic scenarios, but that just provides an intuition. And then we have the goal test. So it's not only important to reach the final state, but I have also a condition that I need to fulfill. So I reach the final state while also opening all the green doors. Then only if I'm opening all the green doors, then I'm finishing the game correctly. And then in here, we're also adding some kind of further restriction just for the use case of the scenario, which is that the game is partially observable. So before I interact with the door, I do not know whether the door is locked or not, or whether some door is actually winning or not. And then definitely, given that choosing one door or choosing the other is completely equivalent from the player, because you don't have like prior information that could help you, then there are 1/6 chances of opening the correct door, and 5/6 chances of opening the wrong one within the same room. And that is actually going to be the use case scenario that we're going to discuss. But before I progress, are there any questions related to the things that I was telling you before? Because then we're going to apply the prior knowledge to this game. Questions? So this is actually something that was not stressed enough, I suppose, from automata theory, which are automata for us are going to be deterministic. But the notion of determinism, let's do like this. The notion of determinism is actually completely unrelated to the notion of probability in this scenario. I might have like a stochastic network, which is still deterministic. So what do I mean with deterministic action? An action is deterministic if by performing this specific action, I'm always going to one specific state. And then those two states might be not equivalent. So maybe I'm performing one action, and then depending on a random chance, either I go to one state or the other, but always doing the same action. But then in one scenario I might win, for example, eventually within the game, because I'm branching out. In another scenario I might not win. So in our assumption, we're assuming that when we are defining an automata, you can only have one outgoing edge from one state to the other with one specific label. Otherwise, the automata becomes non-deterministic, and still, it is quite manageable to create a deterministic automata from a non-deterministic automata, but then you need to know automata theory, but you didn't do compiler theory, so it doesn't make any sense. So let's just assume that all the automata are deterministic, which are then more tractable. Okay? That is actually the notion of that. So that is why we mean with deterministic automata. So let's discuss a very trivial scenario first, and then let's complicate that through GAP. So whenever you see scenario 1, scenario 2, then even in the code base, you'd have scenario, first scenario, second scenario, blah, blah, blah scenario. So you have all the classes implementing this. So they are providing like practical experience of the things that I'm discussing theoretically in here. So in the first scenario, the thing that you're doing is you have the same configuration, but you have that all the incorrect doors, so not leading to the final goal, are actually going to be locked, and the only doors that I'm unlocking are the ones that are leading to the success of the game. So the consequence would be that I can never transit from one state to the other by taking a wrong door and as a consequence arriving to a final state without taking the correct door. So I'm always transiting from one state to the other in a successful way, and so I'm always guaranteed to win. So in this scenario, the thing that you have, and that is actually important. Otherwise, as per prior assumption, you might also, if all the doors were unlocked, for example, and only some of those are leading to the next one, then you might arrive to the final state, but you are not winning the game, and you need to backtrack then eventually again to the first state and collect the correct set of combinations. So then the consequence is that you are limiting the set of actions to be very narrow, and you're guiding very much the player on what they need to do. So the consequence is that in the best case scenario analysis, then I'm always taking the door which is actually the correct one, so I'm always traversing the green edges. In the worst case scenario, I'm hitting all the wrong doors in one room before getting actually the correct door, and then so on and so forth. I'm transiting and doing the same stuff. And that boils down to 18 doors that are visited all together. And so you see that actually that gives you the amount of difficulty of the game, which is actually the minimum set of turns being required for finishing the game and the maximum set of turns. Then we're going to also see that from another perspective, probabilistically speaking, in the next set of lectures. Any questions related to this? Because it's very important to understand the easiest bits, because then we're going to complicate that. So in here, we're using no strategy for fulfilling the game. And we have all the doors that are open, even the ones that are not leading to a successful. So similarly to before, we are picking one door, and all the incorrect doors are left open. So that is actually the change. If we reach the final state as 3 through at least one incorrect door, then we're failing, and we backtrack to the initial state S, and we keep the same 3 correct doors. So that is actually important. Why is that important? So if the game is not reset, and I always have a chance of learning from the environment, from my own mistakes, and then figure out which is actually the correct configuration. So then in here it's going to be better to understand actually what does that entail. So even in here we have, then we need to think probabilistically speaking as the combination of doors that you need to hit. So how many combinations are there? And which is actually the only possible configuration. So I have 1/6 probability of picking one door in one room, 1/6 probability for picking the correct door in the second, 1/6 probability of picking that in the third room, and therefore I'm winning. So I have 1/6 cubed as our overall probability of taking the correct configuration. As a consequence, as per probabilistical theory, 1 minus the probability value gives you the probability of the opposite event. And so you have like 215 over 216 chances of losing. So then you are increasing to 115 the numbers of configuration that are losing. But if you're not adopting a strategy, and that is actually the key point, in the worst case scenario, you might stubbornly try the same configuration that doesn't lead to an acceptance state, or in the worst case scenario, you're always taking configuration of doors that are not leading to winning, and therefore you might be stuck in a live lock. So even though probabilistically speaking, if you're using like a randomic algorithm, eventually you might lead to the final state, and you might lead to acceptation, but that is actually different from worst case scenario. In the worst case scenario, you're not going to have like an average behavior, but you're going actually to take one choice stubbornly enough, always the wrong one, and so you are never going to fulfill the game. And that might give you also an understanding why providing like positive feedbacks in game might be relevant. So maybe a player might be stuck stubbornly, and then by adding this information, you might help them progressing within the game. And still the best case scenario is actually the same. So I'm only picking 3 doors, and that leads to 1/6 probability. And that is going to be different, as I was mentioning before, if I want to adopt a strategy. And this is actually implemented in the code base. So I'm not going to do this interactively because we have only 15 minutes left. But I'm going to guide you on the understanding on how might I build up a strategy to do this. Then the idea is we're always keeping the same 3 correct doors, but I need to backtrack. And so I might win the game if I have, intelligently enough, a notion of memory. So if I'm remembering that a given combination doesn't lead to an acceptance state, I might rule that out, and potentially I know that these 3 doors altogether are not leading to an acceptance state. But I know also something more. It is not necessarily, let's say, yeah, so in this scenario, it is also related to which doors am I picking. And it is actually, then I'm forced to follow a specific order. So I always know that I need to start from one room to the other, basically. So I'm forced to keep the order. So how could I then eventually know that I would need to discard one door? Because actually the acceptance state is actually dependent on picking all the doors all together that are the correct ones. So if I'm fixing one single final door, or the same single initial door, and then I'm doing all the possible permutations of the other doors, then I also know that, for example, if I do 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 3, 1, 1, 3, 1, 1, 4, 1, 1, 5, 1, 1, 6, and then 1, 2, 1, 1, 2, 2, 1, 2, 3, so on and so forth until I reach 166, then I know, okay, maybe I have some kind of information that D1 is actually not the correct door. Otherwise, if there might have been, among all of this, a possible configuration for which actually I would have won the game. Because if, how do you say, if D1 was actually an acceptance door, leading to an acceptance state, then I was analyzing all the possible combinations of all the doors for the other two states, and then I could rule out this door as not allowing you to win the game. And so symmetrically could also do the same kind of reasoning if I'm fixing the same final door and then I'm changing the permutations of the other. And that is also implemented in the code base. So you have something very convoluted, but basically is going to do this. Let me show you. So if you are interested in this, then you have like third scenario, which is actually implementing this configuration, where I'm using actually a strategy eventually, and then I'm remembering all the possible choices, and I'm setting up actually an algorithm to do that. So that is actually hard code. That is not something painstakingly intelligent, but is actually giving you the notion of what a human player might do in order to figure out a strategy to win the game. And then, given that you are providing an algorithm that might encompass a human strategy somehow. And then the handouts that I provided should also help in understanding the code base, which is actually not going to be used as a disclaimer, otherwise you might spend a lot of time trying to understand, which is actually not crucial at this point. This code base is not going to be used in depth for the remaining set of slides and lectures, but this is merely as an understanding exercise and seeing some code and understanding what that does. And the code base is more if you have problems understanding the underpinning theory. So you have like a practical, okay, now it runs, I experienced this behavior, so that is actually what it meant. So it's more like a guiding tool to be used rather than something to be understood. So as I was saying, then as a consequence, I know that I'm failing still in the worst case scenario, a cube of 6 minus 1, but by using a strategy, then I'm avoiding repeatedly seeing the same combinations of doors all over, so I'm avoiding the live lock state as much as possible. And that is actually the key difference with the previous scenario. Before I progress, any other question? Related to this? Yes?
What do the symbols here L mean in the scenario?
Yeah, it's just a variable which is related to the door that I'm considering in each combination. So it's like saying we might get that each single door DI, so it's a generic door number, DI. We might get that each pair of doors DI and DJ, so you see I and J is just saying door I, so it's just the number of the door. And the idea is that, is that correct? Okay, so and in there, the only thing that is actually saying, each pair of doors I and J at a given state H, and K with A is not correct, but there is being saved to enter at a given state. So in there, the thing that I'm saying is, I know that the door that is going to win is actually L, and I know that I'm taking some doors. So H, K, and L are just number of doors. And they're just providing like a formalistic interpretation. But if you are crossing out all the formal parts and you're reading it like just the plain English, we might guess that each pair of doors at a given state is not correct after visiting 6 failing doors at a given state. It should also make sense. Does the sentence make sense even without the math? Okay, but it's actually the important part. The other part is just to quantify and to enumerate and to say the door, which is now KH or something like that. But the idea is that are just variables. You see, it's just making sense even without the math. Good question, by the way. Any other question before I progress? Yes.
So we don't know what the correct path is until we reach the end, and at which point we know that like it was or wasn't the correct path.
Exactly.
And then we go back to the beginning,
Yeah.
and then like we store in like a memory
Yes.
the doors that we've traversed, and then we like don't repeat that same
Yeah.
path that was incorrect.
Definitely. So actually the code base of implementation and keeping track of that, not by storing necessarily all the set of triples, because actually that might require you to eventually summarize the information, but I'm also storing in dictionary the association between like the initial doors and all the possible configurations. And then when I know that I reached one door, initial door was associated to 36 configurations, then I know that the initial door needs to be ruled out in the next tryouts. So that is actually what it's doing. Furthermore, is actually using a random number generator in order to pick which are going to be the doors 1, 2, and 3. But the thing that the code base is doing is also saying, okay, this door was already picked, and then the underneath storage is telling me to discard this door. Then please generate another random number. So that is actually what the code base is doing. Definitely. Then you have a notion of memory. That is going to be implemented by using dictionaries. So you're going to associate one door to the other combinations, or two doors, a pair of doors, to another combination. But yes, so basically that is what the algorithm is doing. Good question. Any other question before I progress? So, just to clarify on the previous question, both stating what HK are. So you see here in the code base, you're going to have like I, J, and K, which are going to be like attempts at opening the doors. So those H and Ks are actually referring to these variables, more or less. And in here, I'm going to use tryouts, and then, how to say, in here, I have like this kind of dictionaries, as I was saying. So I know, for example, that I have like all the possible pairs that were used, and for example in here I have, for example, all the pairs of doors that I'm using and the other door that I was considering. And then if I know that 1, 2, and then I have like 1, 2, 1, 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, then I know then what is actually the size of the other hash set. Then I know that, which is 6, then I know that I could rule out the 1, 2 as a set of doors that I want to generate. So I'm avoiding this kind of scenario. And that is actually what the code base is doing. So you have everything implemented in here. And then the handouts are going to help if you need to better understand what actually the code is doing. In here, and then we're making also things more complicated, you see, because now we are avoiding somehow the possibility of the player to create a strategy. Why? Because if we are not providing the player the possibility of remembering which was correct, and we're constantly changing the correct configuration, then I will be never able to build up a strategy because I'm completely acting at random, and there is no pattern or no rule on how I'm changing the door configurations after something was discarded. So if when I'm backtracking, I'm also changing the configurations of the correct doors, I could never apply a strategy, and so in the worst case scenario, I will be always in a live lock. So live lock is a difference from deadlock. Deadlock in theoretical computer science means that I'm not doing anything at all, I'm dead, and I'm stuck. Live lock is I'm doing something, but I'm not progressing. So that is actually what a live lock is in theoretical computer science. And so, as a consequence, the game becomes episodic, because no matter how I choose the rule, the goals before, then I cannot build up a rule for applying a strategy in the next configuration. So all the information that I acquired to know whether a given configuration was effective or not is completely pointless. So I was filling the game, and then I need just to pick at random, as their behavior of environment is randomic itself. So in here, I cannot do too much about it. But there are other ways to make like the game more plausible. So in here, I'm just providing like an assumption in the multi-hole problem, which is actually a very interesting problem, which is quite very simple probabilistically speaking, but generated a huge amount of discussions in the 70s and the 80s, even throughout mathematicians and philosophers. So that's why it's actually a very simplistic problem, but actually quite complicated if treated trivially. So in this scenario, let's suppose that I'm not only picking one door, but I could also have the possibility of knowing whether something is going to lead me to winning or not. So the thing that this game will do, the multi-hole problem, which is actually a game from the US, is whenever I'm picking one door, then I have two scenarios. Either so I'm choosing one door, but the opponent, which is actually in the case, it is actually the presenter of the quiz or the show, is not opening your door already, so you do not know whether you won or not. But is actually going to open one of the two other doors. So if basically you are picking the car, it's going to open one of the two gates, and definitely if you opened you choose one of the goats, which are not the prize, which are just the failure in here, you want to have the car in this scenario, then they're going to show you the other goat. So this eases enough the game, so it makes more advantageous to change the door, because you only have one use case scenario, which is when you picked the car, which is going to be like detrimental to change the door. While on the other hand, in the other scenarios, if you're always picking a goat and then you're deciding to change, then probabilistically you will always lead to a car, to the prize. But still, so what is actually the idea? But yeah, okay, Giacomo, you're saying that, but if you picked the door from the very beginning, then you would have the prize. But yeah, if you pick the car immediately and then you're not changing, still you have one of the third, or one of the three of probabilities, 1/3 of probability of winning. So, but you need to know whether you were holding the car or not. And that is actually the information that you do not possess. So you're risking something, and you're risking to lose, but the only thing that you know is going to be, the only thing that I know, given I have no priors related to the doors that I picked, then the only thing that I could know is it's going to be more advantageous to switch the door than anything else. So that could also be generalized. So how does that apply to our setup? So even in this scenario, then we could pick and we could change the problem. So we are going to show to the player which are our losing doors after picking the door, and then randomly I could make the player choose one of the other remaining doors. So what is actually the intuition? The more the doors that I have, and the more the doors that I'm going to show to the player, then as a consequence, the greater will be the chance of winning if I'm switching the door. Then I'm not going to dwell into formalisms, which are also available on Wikipedia if you want, and maybe I should also provide some kind of shorthand notice in the slides, so in the handouts, but still, at the end of the road, the winning probability will be adding up to this kind of value that you have down below. So in here is going to be similar. So if you're always stuck to your decision, you have 1/n. But if you're deciding to show your opponent some other doors and you are picking one of the remaining doors, which are not the winning ones, so you're showing the player always non-winning doors, and then you're switching to some other remaining doors, just as clarify, then you will always have a probability which is greater than the other one, and the value is going to be that one.